All right, welcome back. Today we're going to be doing potassium channel gating. You probably ask yourself, well, why the hell do I need to learn this? Well, it's in the textbook. You may be tested on it, you may not. I'm not sure. But yeah, I love Rick and Morty. So like Rick and Morty would say, I don't know. And Rick would be like, shut up, Morty. Just learn. So potassium channel gating. All right. So we have three circumstances here. We're going to go one by one in order. So the first is when the voltage is at negative 65 millivolts. This is like resting membrane potential. Notice we have one gate here. Sodium channel had two gates. The potassium channel only has one gate, and we call it the N gate. When the voltage is at negative 65 millivolts, and when the cell's at rest, the channel is closed. The gate is closed. So no potassium can go outside the cell. Remember, there's more potassium inside the cell than outside the cell. So by properties of diffusion, potassium would want to go outside, but it can't because the gate's closed. So the potassium is essentially going to remain inside the cell. Now, at depolarization, so right at the point of depolarization, say we reach the threshold and we basically start depolarizing, the channel is still going to be closed. Yes, it is a voltage gated channel, so it should open by voltage, which it does, but it's very interesting why it's not open. The reason is because the potassium channel, it does open by voltage, so it's voltage gated, but the main thing about it is it's slow to open. Sodium channels, when exposed to depolarization, when the voltage changes, it opens up immediately. With potassium, the potassium channel, it opens very slowly. So given in time. And I'm going to show you the graph, and it's going to make more sense about what I'm talking about. But all you need to know is that depolarization, it's closed. So the N gate is closed. Now, so say we want to, we depolarize, and now we're back at negative 50 millivolts, after the depolarization happened. The gate is open. What I'm trying to prove here is that the potassium channel takes a while to open. So potassium can now go outside the cell. You're probably still confused, which wouldn't blame you because it's a little tricky without the action potential graph. So I'm going to draw that. So let's do that. Okay, so the action potential graph. This is millivolts. So this is time. This is 1 second, 2 milliseconds, 3 milliseconds, and da da da. We just got negative 65 millivolts, negative 50 millivolts, 30 millivolts, or that's 0 rather, and plus 30. Okay, so we're at resting, as we said, and then we're going to get our EPSP, and we get our action potential, da da da, like that, and we go back down, and so. Okay, that's kind of messy, but whatever. So this is our depolarization, right? We're going up in voltage. So this is when sodium channels open. And this over here is our repolarization. We're going down. This is when our potassium channels open. Okay. Now notice in this over here we said 5 milliseconds at depolarization, right? After depolarization. So this would be like all the way this way. What's the point? What am I trying to say here? Okay. This is basically at the last point where it's open. It begins to open around, positive 30. So the potassium channel is open at positive 30, but it takes time to close. It's all the way open, past 2 milliseconds, all the way to 5 milliseconds. So we said at, negative 50 millivolts, right? At depolarization, it's closed, but negative 50 after depolarization, it's open. Well, we're at negative 50 here. Let's go trace the line. Okay, this is at depolarization, right? This is the second scenario. It's closed, which it is closed, right? Sodium channels are open, potassium is closed. And then we go further at -50. And oh, we reach after depolarization because this is repolarization, right? This is after depolarization. We're at -50 millivolts, and it's open. It's open. Let me erase this and let me make this like at 2 milliseconds. I think it'll make more sense. It's the same thing. You just need to realize that it opens after depolarization. So the interesting thing you need to learn is, the one thing you need to get away from this is potassium channels open more slowly than sodium channels. The, what is true is potassium channels close more slowly than sodium channels. Okay? This is very important for you to understand, what's the reason behind this? The reason behind this is we have our, usual action potential, right? If they did not, if they did not open at separate times, say if the sodium channel and the potassium channel opened at the exact same voltage, okay? They open at the exact same voltage. There's no break between, right? Potassium did not open, more slowly. Well, what would the action potential graph look like? Well, it would actually just be a flat line, right? Because there's ions going in and ions going out at the exact same time. It's going to be like net zero. It's going to be the potential is going to be the same. If you have the same amount of sodium ions going out and the same amount, the same amount of sodium ions going in and the same amount of potassium ions going out, the voltage is going to be the same. So we would get no action potential, no signal would be generated. And you can see how that would be a bad thing. If we need our body, to respond to something, well, we can't because there's no action potential. This is why there's a delay. It's because we get this action potential, we get the spike, and then we can go back down due to potassium channels opening up later. So that's basically it. I hope this was easy. I hope this was useful. And yeah, I love you guys. I'll see you guys later.